target object. So we can render the target object from the viewpoint of the projectors, and then have to solve how to balance the two projectors and find out which projector should project onto which portion of the target object. And with this, we can augment any object. So why is this blending so complicated? So the problem here is that depending on the target geometry, we get different interaction scenarios between pixels, which you can see here, and this dramatically changes over the surface of the target object. So let's have a look at a concrete example here. So here you can see the interaction matrix, and the first ray here misses the target object, so no entry. The second ray hits the target object, but the surface point doesn't get hit by the other projector, so we just have this one entry here. The next three rays hit the target object, and the resulting surface point also gets illuminated by the other projector, so we get two entries. And the most interesting case is this one. So all these three pixels project onto surface points which are hit by the same pixel from the other projector, and you can see this here. So this really brings the globality into the problem, because over the surface of the object we get a lot of these positions and scenarios, and they will be all over the place. So what we have done, we have implemented a optimization problem, and this ELI term here is basically the matrix you just saw, with the matrix entries being Lambert's cosine law. So here we model the physical properties of light. And we have additional terms, so we have a regularization term, and we have a balancing term based on expected projection quality, and also we have to keep the luminance between 0 and 1. So let's have a look at the last two terms here. So we always want to give the projector the edge which will give us the best projection. So for example, for the green projector, depending on the incident ray direction onto the surface, we get different pixels footprints onto the surface. And if the ray hits at a perpendicular angle, we will get the sharpest projection possible. So if we have multiple projectors, we always want to give the projector the edge which gives us the sharpest projection at this surface point. And of course we have to keep the luminance between 0 and 1, because that's all a projector can do, and we use this Barth function for this. And the resulting problem is quite large. It's a large nonlinear optimization problem, and to solve this we implemented a Gauss-Newton solver on this GPU, and for updating the Gauss-Newton solver we linearize the problem around the last solution and compute the update with a conjugate gradient method. Then we do a little bit of parameter reprojection to be stable between 0 and 1. And this is solved on the GPU completely in real time. So this is why we have this dynamic setup. So here you can see some results of the system. So with this we can project animation sequences onto our object. We can let the object appear to be a perfect mirror by having a light probe. By adding viewer tracking, we can render something on the inside of the object, which looks really cool. And we can also use this for product design and marketing purposes here with Adidas. So these were our results last year here at Siggraph Asia. And this Monday here we presented a short paper where we tackle some problems of projection mapping. So for example, we showed how we can get rid of interreflection on the object to get a better contrasting projection. We showed how we can get rid of environment light and how to get rid of black level, and you can see the results on our booth over there. So with this system in place, we now want to add painting to the system, right? And for this, we use the Razer Hydra, which is a magnetically tracked device, and we calibrate it into our system. And it feels a little bit like an airbrush pistol, so it loosely mimics airbrush painting. So, and with this we want now to paint on the object. So how does this work? We have our target object and we want to paint on it. So for that we have to find out which surface points or which texels are hit by the brush. And for this, we rasterize the object into its own UV space, and by that we get a fragment shader for every texel or for every surface point, and we can test for every surface point if it's part of the brush. This works quite nicely, but there's still one problem remaining. By the simple test, we get every texel that's within the view frostum of our painting device. So you could